Hi, I am V. Boshin. I am third-year PhD student at Johns Hopkins University. Today, I am honored to present my work on mask-free OVIS, Open Vocabulary Instance Segmentation without manual mask annotations. I did this work when I was interning at Salesforce. I would like to thank my mentors and all my collaborators for their constant support throughout the project. Instance segmentation is a computer vision task that involves identifying and delineating individual objects within an image, usually by assigning a unique label to each pixel corresponding to a specific object instance. Instance segmentation models are typically trained on a predefined set of closed set classes. However, in a zero-shot setting, where new or novel classes are introduced, these models fail to segment instances of those classes accurately. To address this, we propose leveraging a pre-trained vision language model and image caption pairs to generate pseudo-box level and pixel level annotations for both base, known and novel, unknown classes, enabling our pipeline completely free from human-provided annotation. Further, benefiting from pseudo-labels, our method sets up SOTA performance for both detection and instance segmentation tasks compared to recent methods trained with manual masks on MISCOCO and OpenImages datasets. Instance segmentation is a computer vision task that involves simultaneously detecting and segmenting objects in an image, and MASK or CNN is a popular framework for accomplishing this task by combining object detection with semantic segmentation to generate precise object masks. To establish ground truth for instance segmentation, two key requirements are necessary: bounding boxes that accurately enclose each object instance, and pixel-level annotations in the form of instance masks that precisely delineate the boundaries of each object within an image. Achieving state-of-the-art performance in downstream tasks such as instance segmentation requires large-scale datasets with human-annotated samples and extensive human effort. Even for new, novel categories, the process of human annotation becomes necessary once again to train models effectively and accurately on these novel classes. Therefore, in our work, we propose a method that leverages image caption pairs to generate pseudo-box level and pixel level annotations. By utilizing a pre-trained vision language model, we can generate pseudo-mask annotations for both known and unknown classes. Thus, we make the following contributions. Firstly, we leverage image caption pairs in a pre-trained vision and language model, VLM, to generate pseudo-mask annotations for objects of interest. Secondly, we utilize these pseudo-mask annotations to train an instance segmentation model, eliminating the requirement for human-provided box-level or pixel-level annotations. This approach significantly reduces the need for labor-intensive manual annotation, making our method free from human-provided annotations. Previous methods typically learn task-specific information, such as detection or segmentation, using fully supervised approaches, while incorporating weak supervision for novel categories. However, the disparity between strong and weak supervision signals during training often leads to overfitting and necessitates costly annotations for the base categories. In contrast, our method tackles these challenges by generating pseudo-annotations for both base and novel categories using image caption pairs under weak supervision. This approach effectively addresses the issues of labor-intensive annotation and overfitting, offering a more efficient and practical solution. While the Region Proposal Network, RPN, is commonly employed to generate proposals for novel classes, its reliance on fully supervised learning with bounding box annotations often causes overfitting towards the base classes. As a result, the proposal generation performance for novel classes suffers. In contrast, the Weakly Supervised Proposal Network, WSPN, trained with weak supervision using image labels, surpasses the performance of fully supervised or PN by producing higher quality proposals for novel object categories. This approach effectively mitigates the overfitting issue encountered by our PN on base classes. Illustrative overview of our pseudo-mask generation pipeline. Given an image caption pair and pre-trained VLM, we generate an activation map for the object of interest, umbrella, and enhance it using iterative masking strategy. We generate box-level annotations using an activation map as a guidance function to select the best WSPN proposals covering the object. We crop the image corresponding to the generated pseudo bounding box and perform weakly supervised segmentation to obtain pixel-level annotations. The pseudo-mask generation consists of three steps: GridCom activation map generation, pseudo-box generation, and pseudo-mask generation. Given an image caption pair, we first generate a GridCom activation for the object of interest, leveraging the localization capability of a pre-trained vision language model, in this case, Zebra. To enhance the activation map, we employ an iterative masking strategy, wherein the most active regions are replaced with the image mean, followed by recalculating the GridCom map. 4. Weakly supervised proposal generator. We follow Genettle weakly supervised object detection framework where we train the proposal generator with image labels in a weakly supervised manner. Once we get the proposals from WSPN, by utilizing the activation map as a guidance function, we select the best proposals from a WSPN that effectively cover the object, thus generating box-level annotations. Following the generation of pseudo-bounding boxes, we proceed to crop the image based on these boxes. Subsequently, we perform weakly supervised segmentation to obtain pixel-level annotations. This is achieved using the weakly supervised segmentation WSS network, which generates binary segmentation for each cropped instance by training on a small number of points within activation regions as foreground and a few points outside activation regions as background. Here we present examples for WSS output segmentation map and WSS loss function. And here, we present generated pseudo-mask visualization. Lastly, the generated pseudo-mask annotations are employed to train an instance segmentation model, eliminating the necessity for manual box-level or pixel-level annotations provided by humans. Our method achieves state-of-the-art performance in both detection and instance segmentation tasks when compared to recent methods trained using manual masks on popular datasets such as Ms. Coco and OpenImages. In the top row, we visualize mask or CN and predictions trained on pseudo-masks generated from the Coco dataset. Similarly, in the bottom row, we show mask or CN and predictions trained on pseudo-masks generated from the OpenImages dataset. Through training, mask or CNN effectively learns to filter the noise present in the pseudo-masks, resulting in improved quality predictions with complete masks and accurate, bounding boxes. In the top row, we generate activation maps using GridCom by providing Coco captions and the objects of interest, such as zebra or giraffe. Similarly, in the bottom row, activation maps are generated using GridCom with pseudo-captions generated from image labels and the same objects of interest. Here, we can observe irrespective of caption type is robust and generates accurate GridCom map. Thank you all for your attention throughout this presentation. Please scan the QR code for further details regarding our project. Thank you.